Hello and welcome back. This is the first video for section 14.3 where we'll be talking about motion in space. In this very first video, we are going over position, velocity, speed, and acceleration. So these are some of the most important objects to be studying when studying motion in space. Really everything sort of depends on these sort of big three. Of course, there's higher derivatives we could take besides acceleration, but we mostly focus on these three because these are the most relevant to most people. So of course, we'll let our position function, r of t, remember this is a vector valued function, plug in a point in time t, and out comes a vector. We can think of that vector having its tail at the origin and head at the point on the curve, so pointing at the object. So this is telling us the position of the object at any point in time. If we take a derivative of that vector valued function, we get its velocity. Remember, this points in the direction of motion, and the magnitude of velocity is the speed. So the longer the vector, the faster the object is moving. We can get the speed function by just doing magnitude of v of t. And this is, I want to remind you, a scalar valued function, right? This is a scalar valued function. And then if we take another derivative of velocity, we end up with, of course, acceleration. So while we have a nice intuitive understanding of how velocity relates to position, right, direction of motion and speed of motion, acceleration is a little bit harder to visualize. So let me go ahead and jump to an interactive figure. And I'll sort of give you my rundown on how to think about acceleration. So here we have this object moving along this sort of funky curve, right? And here we are at, what time value are we at? Let's move to t equals 0. So t equals 0, we're right there on the curve. And let's see, let's increase the time value. Let's see how this thing moves in time. There's r of t changing, pointing along the curve. So we're moving this direction along the curve. We're going to do this loop-de-loop here as I keep increasing. And I do want to end up on the other side of this loop-de-loop to talk about this curve coming up here. So, right, so velocity, hopefully you should be able to picture what the velocity vector is going to look like at, let's say, this point on the curve. So it should be tangent to the curve there and pointing in the direction of motion. And then its magnitude will be the speed at which it's traveling. So here's our velocity. And we like to put the tail of the velocity vector where the object actually is on the curve, right? So this is just sort of convention. Remember that the vector v of t could be anywhere in 3 space. It's not telling us anything about the position of the object. It's just telling us the velocity, right? It's just a vector, and vectors are the same no matter where you put them in 3 space. So right, that should resemble what you thought it might be. And then let's try and visualize what the acceleration vector is going to look like. So in order to visualize that, I'm going to keep increasing t here, and instead of focusing on how r of t is changing, how the position's changing, focus on how the velocity is changing. So notice the velocity it was starting off going this way. It's now moving sort of to the positive y direction and positive x direction a bit more. Or rather, yeah. And also in the negative z direction, right? And as we go around this curve, it's going to be pointing more and more in the negative z direction. And the x direction, it's now starting to point in the, it's not quite pointing in the negative x direction, but it's changed from pointing in the positive x direction to almost having no x component here. It has a really small positive x component there. As we move, it's going to get less and less. And now notice, now it looks like it has some negative x component, right? It's pointing a bit to the right here, so that's a negative x component. So it went from positive x component to negative x component. And so what we're focusing on is the change in the velocity. So how's this thing changing? Well, it's going more and more in this direction, to the negative x direction. So let me go ahead, I'll back up a little bit here and plop the acceleration vector down. And as we can see, it's pointing almost directly in the negative x direction, right? So that's telling us this velocity vector is starting to point more and more that way, right? Acceleration is the rate of change of velocity. So that's the idea. We can keep kind of going with this and just see how this curve goes as we move along. Accelerating, Accelerating that way, still accelerating that way as we move along. Notice that around this curve, it's high positive y, and it looks like as we move along this curve, it's sort of flattening out in the y direction. So we should see the acceleration vector start to point in the negative y direction, at least a little bit. It's actually becoming quite long now. It's accelerating quite a bit as we round this curve. And notice it's starting to point just a little bit in the negative y direction, which is going to change the velocity. It's going to start to flatten it out in the y direction. So that's the idea. Let's work through an example. So one thing to point out here is that acceleration, right? There's sort of two ways that an object can accelerate. One comes from change in speed, right? So if my object starts moving faster along the curve, then the acceleration, that'll contribute to the acceleration. We can get a change in speed, or we can have just a change in direction. So it's possible my object it's not changing speed at all, it's going at a constant speed, but if it's changing direction, that means the acceleration is going to point in the direction of that change. That's the idea. So to illustrate this, let's work through an example. Here we have our position function given by 3 cosine t, 3 sine t. We've looked at an example similar to this before, right? We know that this describes circular motion. And this is just in 2 dimensions, right? If we wanted, we could add a 0z component here and plop this in 3 space, but it's fine to just think about it in 2 dimensions. So we know this is circular dimension, or circular motion. And in particular, its radius of the circle is 3 and centered at the origin. So let me go ahead and plop down 3, negative 3 in the x, 3 in the y, negative 3 in the y, x, y. So the motion of this object is going to look like circular. Right, this is circular motion. It's not a perfect circle that I've drawn here. Let me change this maybe a little bit. Let me move this down here. It's more like negative 3. But so a perfect circle that it's moving in, not as I've drawn it. Let's see. So right, we know that at various time values, I want to plot a few different time values here. I'm going to plot t. Let's do t equals 0, t equal pi over 2, t equal pi, and how about t equal 3 pi over 2? I just want to plot those. So position at t equals 0 should be 3, 0, right? Plugging in 0 for t. I'm going to go ahead and plot that in blue. So my blue is like my position. And so that is r of 0 is that vector. R of pi over 2 will be here. Again, you can recover that by just plugging in pi over 2, right? Cosine of pi over 2 is 0, so I'll have a 0x component, 3 in the y component, and I can plot that. Right, this is why it's moving circularly. R of pi will be over there, and finally r of 3 pi over 2 will be here. Now let's go ahead and get velocity. So before we actually do the calculation, think about what is the velocity of this object going to look like. I should have a direction, by the way, on the position, right? Remember, these vector-valued functions also have an orientation to the curve. So we're going around in the counterclockwise or positive direction. Going around like that. So how is the velocity going to look at every point? Remember, it should be along the direction of motion, and the length of it should be the speed of this object. So let's go ahead and take a derivative. Let's find velocity. V of t is the derivative of my position vector. And so that's going to be, what, minus 3 sine t and 3 cosine t. There's my velocity vector. We can go ahead and figure out my velocity at these points. So v of 0, that'll be, what, 0 in the x direction, and then 3 in the y direction. We can find v of pi over 2. So now sine will be 0, and I'll have 3 cosine t, cosine, rather 3 pi over 2. So this should be minus 3 now, minus 3 in the x direction, and 0 in the y direction. Right, good. Wait a second. Yeah, I just want to make sure. Cosine of 0. Yeah, good. Okay. We can do v of pi. That would be what? Sine of pi is 0. And then cosine of pi is negative 1, so this will be negative 3 in the y direction. And then we have v of 3 pi over 2. So we're just doing a few points here just to get an idea of how this thing's moving. So sine of 3 pi over 2 is negative 1, so I'll have 3 in the x direction and then 0 in the y direction. And I'm going to go ahead and plot those, and I'm going to put these vectors at the wherever the object is in space. So I'm not going to put it here at the origin, but rather where it is. So v of 0, I'm going to place its tail right here, and it's going 3 in the y direction. So up 3, exactly. So this is v of 0. Pi over 2, negative 3 in the x direction, so it's going here. And this should corroborate with what you had in your head. If not, make an adjustment. Why did you not think it would look like this? Or what did you think it would look like? Why is it not turning out that way, right? These are important questions to ask yourself if you didn't quite have the right intuitive response to this. And that's okay if you didn't. This is how you learn things, is you make conjectures. If they turn out right, that affirms your intuition. If they turn out wrong, means your intuition needs to change. So there are my velocity vectors, right? They match up with this, and it should match up with what you're thinking. Notice that at every point, the velocity, or the speed rather, the magnitude of the velocity is 3. Is that the case at every point on this curve, or just at these 4 special points? And how do we know, right? How do we know if it's going to be like that for all points? Well, to figure that out, we should find the magnitude of the velocity vector. So what is the speed? Let's ask ourselves that. What is the speed of this object? Let's find magnitude of v of t. So we've already calculated v of t here. So this is going to be square root of what? 9 sine squared of t plus 9 cosine squared t, right? X squared plus y squared. Sine squared plus cosine squared is 1, so that's just going to leave 9 here under the square root, and we get out 3. So now that we've used the general form for velocity and found the speed of that, we can see at every point on the curve, we will have a speed of exactly 3. So at any point, my velocity vector will have a length of 3 along this curve. Okay, so that's pretty cool. This is constant speed. So that means any acceleration that's happening here is coming just from the change in direction of velocity. And there certainly is a change in direction and velocity, right? Straight up to straight to the left, to straight down, to straight to the right, back to straight up. So what is the acceleration at each of these points? So if I say, let's pick here, let's find acceleration. Let's go ahead and find a of t. So that's the derivative of velocity, or second derivative of position. Velocity. So let's take a derivative of this one. We get minus 3 cosine t, and then minus 3 sine t. Now notice something special here. Here's my position, 3 cosine t, 3 sine t. This is minus 3 cosine t, minus 3 sine t. So it's the negative of position. Now isn't that interesting? This is something that's special that happens with circular motion like this. I'll do acceleration in green. Remember, I did velocity in red, and I did position in blue. If you can see colors, that is. It's not going to... helpful for those that can see it sometimes. So I'm going to go ahead and plot this at these points. So here is my r of 0. So negative r of 0, which is a of 0, will be just pointing in the opposite direction with the same magnitude. So there's a of 0. We'll have a of pi over 2. My acceleration is pointing to the right here. This is a of pi. And finally, acceleration pointing straight up here, a of 3 pi over 2. So what's interesting here is the acceleration is always pointing towards the origin. So from any point on the curve towards the origin. There is some more to talk about here. In particular, notice that position and velocity are always orthogonal to each other, and then acceleration and velocity are also orthogonal to each other because acceleration is parallel to position. So this definitely has some special properties. Again, I think the big thing I want you to get from this is help you to visualize acceleration, where this acceleration is coming from, right? In this case, it doesn't have anything to do with a change in speed. It's just change in direction. So that can also give us a non-negative acceleration vectors if we're just changing direction. If we're also changing speed, these would look a little bit different. That is... I know. One last thing I wanted to show you. I wanted to jump to another interactive figure. Just the same one we just did, the circular motion, circle of radius 3, centered at the origin. And I just want to plot, that's exactly what we had just drawn, but I want to get the sort of off the special angles, right? And just see how it looks when we're in between those 4 points that we picked out, right? It's still the case that velocity is perpendicular to acceleration and position and acceleration are parallel to one another. Acceleration is always pointing inward towards the origin. And velocity, right, as you can see, the magnitude of the velocity is staying the same throughout. Okay. So that's it for this video. Please join me next time. I'll see you there.